Hello and welcome. In this video we are going to take a look at more modeling with differential equations, and we'll take a look at one of the classical problems which is called the tank problem. We'll do some more model analysis, and we'll also look at something called parameterizations. So mathematical modeling is one of the things I like to spend the most time on because it's the most challenging principles in mathematics, but at the same time it's one of the most important skills to be able to have, especially if you're a scientist, an engineer, a mathematician, etc. This is just something that you need to be able to do, and it takes some time to develop. So to become a strong modeler, of course, one of the most foundational things is to really clearly define the problem. So what is it that you're looking for? What is it that you want to be able to answer? That typically leads us to the unknowns that we have in the problem, so the variables that we're using. Then we often need to have a set of assumptions, something that tells us how things are expected to behave. So if we're dealing with populations, of course populations behave differently than electrical circuits. And we need to know what kinds of things we can assume. So even if we're not experts in the particular field in which we're modeling, then as mathematical modelers, we need to be able to take a set of given assumptions and convert those into something more mathematical. And we often use a lot of dimensional analyses. So units become incredibly important when you're building models. So the easiest way to start is first of all to identify the question. So what are you asking? What is it that you want to determine in the first place? Once you know that, that allows you to then define the variables. And since we're in a differential equations class, we know that we're going to want to be working with differential equations models. So let's take a look at our first tank modeling problem. A 50-gallon drum is initially full of clean water. Water concentrated with 1 pound per gallon enters the drum at a rate of 3 gallons per minute. Salt water leaves or exits the tank so as not to change the volume of liquid in the drum. How much salt will be in the tank after 10 minutes? What is the long-run concentration of salt in the tank? So our question is asking about salt after a period of time. So immediately that tells me, okay, well, I want to model the amount of salt in this tank as a function of time. So I'm going to define some variables. I'm going to say, okay, well, my dependent variable, I'm just going to call it y here, is going to be the amount of salt in the drum. That's what I want to measure. So amount of salt in drum. And we want to specify units because when we write dy dt, we've got to make sure that our units are what they're supposed to be. And so we're measuring salt in pounds, therefore there's no reason why we should convert to a different unit of weight or mass. So that looks good. And then T is going to be, of course, the time since the salt water starts coming in. So we'll just write that. So time since salt water enters drum. And that time looks like it should be measured in minutes since things are happening over the course of minutes in this problem. Of course, we could convert everything to hours, but why would we do that? We're told about measurements that are in minutes, and we're asked questions that are regarding minutes. So to convert to hours and then convert back to minutes would not be highly effective. Now I'm going to build a model for my drum. So I'm not going to draw a big fancy drum, but you can if you want. This is sort of the bathtub analogy. The bathtub analogy says that you have something coming in, you have something going out. We've got to think about what's going in and what's coming out. So imagine that this is the top of our drum. We have liquid entering that drum. So inside of here, we know that this is a 50-gallon drum, so I can label this with 50 gallons. And I also know that y at time 0 is going to be 0. It's initially full of clean water. Initially full of clean water. So I know one of the things I like to put in this is my initial condition that y at time 0 is 0. The amount of salt in the drum when t is 0 pounds. So what I have coming in is I have 1 pound per gallon. So I'm going to write that down here. I'm going to say I have 1 pound per 1 gallon. And I'm going to write my units like this because I want to be able to see how units nicely cancel out. Now the other tidbit I have is that water is entering the drum at 3 gallons per 1 minute. Well, what do I do with those two measurements? One of them, the 1 pound per gallon, that is a concentration. Concentration just means how much weight or mass per volume. So if something is coming in at a rate of 1 pound per gallon, that means for every single gallon of water, there's going to be 1 pound of salt. So imagine that you have a container that contains 1 gallon of water. All right, so there's your 1 gallon. And of course, we're not, it's dissolved inside of here, but let's just pretend for a second that we could separate them. If you could, you would have, for every 1 gallon, you would have 1 pound of salt. Okay, so that's essentially what we're saying here. Now, we do need to define these variables because dy dt, its units are going to be in pounds per minute. So when I look at the net inflow rate, which is the rate in, or the rate of salt in, minus the rate at which salt runs out. So this is just like thinking about water entering a bathtub. The net rate at which your tub is either filling or draining is a function of, okay, well, if your tub is filling at 10 gallons per minute and it's draining at 7 gallons per minute, then 10 gallons per minute coming in minus 7 gallons per minute coming out tells me that every minute I should see 3 more gallons in net inside of that tub. So no different here, it just happens to be pounds of salt per minute instead of gallons per minute. So the rate coming in has to be in pounds per minute. Otherwise, there's no other way that I could subtract 2 units and end up with pounds per minute unless they're both in pounds per minute. So that's going to be crucial. This has to be in pounds per minute, and this has to be in pounds per minute, so that when we subtract them, we still end up with pounds per minute. Here I have pounds per gallon. How many pounds of salt will be added to each gallon? Here's how many gallons are coming in each minute. Well, wait a minute. So if I look at the units here, if I multiply these together, I'll end up with pounds over minutes. And this should make sense because if I have 1 pound every gallon, and I have 3 gallons coming in every minute, that means I'm going to have 3 pounds for each of those 3 gallons across that entire minute. So it's not surprising then that we would have 3 pounds per 1 minute. Now again, this guy here is called the concentration. This is called the concentration. And this is what I like to just call the flow rate. The flow rate. And all that means is how fast the clean, unadulterated water is coming in. And the concentration is at what dose am I putting in this particular chemical. Now what I have coming out gets a little bit more complicated because initially we might think that, well, if you put in 3 pounds and you're pushing the same amount of water in as you are out, because it says here salt water leaves/exits the tank so as not to change the volume of liquid in the drum, we do know that the flow rate out is also going to be 3 gallons per minute. And this way, if you have 10 gallons per minute coming into your tub and 10 gallons per minute leaving your tub, then that water level should never change. It should remain at whatever it was when you started this process. But here's the thing. Those 3 pounds, we're going to make a key assumption here. And that key assumption, and I'm going to put this off to the side, is first of all that the water is always well mixed. So the tank, the drum water, or drum liquid, is always, or instantly well mixed. We'll use that word. And what we mean by that is basically imagine or pretend that you have some sort of propeller in here that just continuously mixes the salt with the water. So you don't have like pockets or patches in here where, let's say, all the salt kind of condenses in this corner and nothing's inside. We're assuming that the second that salt comes in, it's instantly well mixed with everything in there. Now, whether that's a good assumption or not really depends on the context. If this is a lake, then it's probably not a great assumption because there's probably not something spinning it. But if this drum is being shaken, or if there is something in there stirring it up constantly, then it is a good assumption. So we are going to make that assumption in this problem. Otherwise, we're going to have a really difficult time trying to argue about, okay, well, where is the salt? How much is really coming out? So now that we have that underway, if the 3 pounds get mixed in with that, and after 1 minute, you might say, okay, well, 3 pounds have basically made their way in. But they haven't necessarily made their way out because only 3 gallons are coming out every minute. But this 3 pounds that's mixed into this 50 gallons is equally dissolved inside of here all over the place. And so the 3 gallons that come out are just a really lightly concentrated version of what went in, right? Because 3 pounds is a lot, but not in 50 gallons. So all of that salt doesn't make its way out each minute. And therefore, it's a little bit more difficult to say, well, how many pounds of salt are inside of that tank? And this is where we get to use our variable. The variable that represents how much salt is in the tank is Y. That's the amount of salt in the drum. So in following the same procedure, here we have our flow rate. Now we need a concentration. And the only thing that we do know is that there are inside of this tank, what's coming out is concentrated with Y pounds of salt, right? Because that's how much salt is in that drum. It's not like here what's coming in is consistently, somebody's controlling the dial and they're saying only 1 pound is going to be added for every 1 gallon that comes in. But there are already Y pounds in here and there are 50 gallons. So the concentration of salt in the tank is Y pounds mixed into 50 gallons. This is a much safer bet than trying to say, well, it's 2.9 or it's 2.8 or it's 3. We just don't know. And now that we have this, we're pretty much ready to build our model. Our dy dt is going to equal the rate in, which is, we said 3. And I'm just going to write 3. I'm not going to use the units now because it's already in pounds per minute. Now down here we'll have the same dimensional analysis because here the gallons will cancel and will be in pounds per minute, except in this context we'll have Y times 3, or 3Y pounds, divided by 50 times 1, which is 50 minutes. So this is in 3Y pounds per 50 minutes. It might seem weird at first because you have a variable in your unit, but that's okay. It's just an unknown quantity. And so this will be 3 minus 3y over 50 as our differential equation. And so this is our dy dt.